have to follow there as well. Okay. Okay. So today I'm going to speak about I have to follow here. Operator norm convergence for a sequence of random matrices and some applications to quantum information theory. So that's the plan. There is a slight modification in comparison to what I announced in my abstract. Somehow I wanted to make something which fits between the talk of Guillaume and the talk of Staszek. So I first want to advertise the fact that in random matrix theory, lots have been done about the convergence of eigenvalue counting measure, whose definition I'm going to recall, but less has been done because it's harder, basically, about the convergence of largest eigenvalues, or rather the spectrum of the spectrum of measures. And so I want to give an application in the single random matrix case, and then afterwards two extra applications to the multiple case. So first of all, a very quick reminder about random matrix theory. So random matrix theory, one may say, is just a probability theory, but instead of having complex values or real valued random variables, the values of the random variables is matrices, and there we have some extra multiplication, some extra structure, eigenvalues, and so on. So we can try to play with, each time in probability theory we want to understand what happens in some limit, and here, what the limit that we are taking in general is the limit of the dimension of the matrices that goes to infinity, and what we study, it depends. It could be either the entries of the matrix, but then there is nothing specific about random matrix theory. So rather it's something like the eigenvalues or the eigenvectors. So the eigenvectors is actually a very complicated topic which has started only recently. I'm going to speak about eigenvalues mostly today. So the general notation that I have is the following. In general, the random variable which I'm looking at are indexed by the dimension. So the d by d, it's a d by d random. It's a d by d matrix which could be random. I'm going to assume it to be random, even though it doesn't have to be so at any cost. And all the examples I'm going to look apart once are actually self-adjoint random matrices, which means that actually the eigenvalues, which I call lambda I, ranging for I between 1 and d, I count them with multiplicity, are actually real numbers. So I can order them in the decreasing or increasing or decreasing order. And like I was saying before, the quantity that had been the most studied historically is the so-called eigenvalue counting measure. So there is a delta missing here, but it's so maybe I should. Anyway, I'm going to write down one or two things. So we have mu d, which is 1 over d, sum for I between 1 and d of delta lambda I d. So, sorry?
What's delta lambda I d?
So delta is the Dirac mass at point lambda I d. So there was a delta which was missing. So this is a probability measure of mass 1, which takes the value 1 if I am at point lambda I d, and 0 else. So I'm taking a sum of these d times, and I'm normalizing. So basically, this probability measure here, this mu d, gives me, if I look at a subset of the real numbers, what is the percentage of eigenvalues that fall in this. So this is the eigenvalue counting measure, and I normalize it so that it becomes a probability measure. What I want to do is let d tend to infinity, so it's good if I keep the same normalization. So this is, of course, this makes sense for any matrix, but when I have just a plain matrix, this is a plain discrete probability measure. In the case of a random matrix, this is a random probability measure. So I was saying the classical random matrix question is try to study cases when the random probability measure mu d, which is defined here, has an interesting behavior as d goes to infinity. And a more recent random matrix theory question is how about the support of this measure? So basically just the set, which is the union of all eigenvalues. It looks like it's a simpler object to look at, but actually when we make limits, when we try to understand what happens in the limits, we're working on completely different spaces, and the question of trying to understand the support is actually more subtle in general. One first needs to understand the measure in general before we understand the support. So
Other elementary symmetric functions of the eigenvalues?
in principle, yes, that could definitely be something which one is looking at. People like diachronists, for example, have looked into such a kind of questions. I'm not going to speak about it today, but in principle, any thing you can cook up with random matrix is potentially an interesting object to make asymptotic, to study its asymptotic probability behavior. Okay, so what I will just do is I will first start with the single matrix case. So what I call the single matrix case is I have a model for random matrix, which is for me going to be the Wishart matrices, which I'm going to define. I'm going to tell some application, and after this I will say what happens if I take two copies of it or many copies of it which are independent, and if I start to play with them together, like to multiply them or things like that. So for me, I'm just going to call G the so-called, so historically it's called the Ginibre random matrix. What I just do is I take a D times S. So I'm going to write it down here as well because it's good to keep it. So G, this belongs to it's a D times S. And so this is IID, complex. So I just take standard independent, identically distributed entries, which are drawn according to the standard Gaussian complex probability measure. So it's very simple to simulate on a computer. And well, of course, the problem here with this is that a priori it is in practice interesting to have D and S which are arbitrary. So I cannot speak about eigenvalues. I could speak about singular values. Actually, that's more or less what I want to do by looking instead at W, which is G star. So which now becomes a self-adjoint random variable in MD of C. So I put an SA here, and this is the so-called Wishart. I'm going to call it the Wishart random matrix of parameter ds, and it's one of the most studied random matrices. Actually, Guillaume already spoke quite a bit about it. So we just have these facts here that if I look at the expectation of the diagonal of a diagonal coefficient here. This is S, which kind of makes sense when you look at what it means to make the multiplication. And so if I take the trace, expectation of the trace, this is D times S because the dimension of the matrix is D. So all this lets us think that we need to normalize the matrix in order to obtain something interesting as the dimension goes to infinity. Actually, we'll have to define it by something like a power of some polynomial function of D and S. So this is the probability measure that we will need to introduce in order to study the interesting limiting cases, the so-called Marchenko-Pasteur, which I could perhaps also draw here. So I'm not. Maybe the formula itself doesn't matter too much. Let me rather make some plots of this probability distribution. So you see, when C is small, then I have a heavy weight at delta 0, a heavy Dirac weight at 0. And when C becomes larger than 1 or larger, then there is no more Dirac and there is only an absolutely continuous part. So if C is small, what we have is a big Dirac mass here, and then actually something here around 1, some absolutely continuous part. So now let me show what happens when C is 1. When C is 1, we have, so you see the absolutely continuous part is between A and B, and at C equals 1 exactly, then the left part is 0. So we have actually so the absolute the absolutely continuous part of the probability measure actually does not have this quadratic behavior at its edge anymore. It has a 1 over square root behavior like this. So we have 0 here and we have 4 here. And then when C becomes bigger, so when C is large, what we have is that the first moment of the measure becomes bigger and bigger. Actually, the first moment is exactly C, it turns out, and so we get something which becomes bigger and bigger like this. And actually, when n is very large, this is actually, if you center it properly, this, I mean, either when C is very small or C is very large, this actually looks very much up to some appropriate normalization, like a so-called semicircle distribution, so some kind of half.
But C is 1 plus epsilon. Where is it supported?
For C equals 1 plus epsilon, this would be something like this. So it starts to be something like this. Yeah. So it's always supported. Yes, I should have said it as well. It's always supported on the positive, on the non-negative real numbers. Actually, what I'm going to say in 1 second is that if you look at this eigenvalue distribution for this model, if you take some right parameters, that's going to be the asymptotic behavior. So let me introduce some notation for the purpose of that. Okay. So, well, here I have some notation. So here we have some permutations. Some permutations. Some k by k permutations. So I have this full cycle which I call gamma, which sends 1 to 2, 2 to 3, and so on and so forth. Then I have, for a given permutation, I have absolute value of alpha, which is its length in the Cayley graph generated by transposition. So in other words, the minimal number of transpositions that I need to generate to obtain alpha as a product of transposition. So it's known to be k minus the number of cycles of the transposition. And so since it is a norm, we have this triangle inequality here, which is the geodesic inequality. It turns out actually the difference between the left-hand side and the right-hand side is a multiple of 2, and we have this So if I look at the difference divided by 2, it becomes an integer number, which is known as the genius of the permutation with respect to gamma here. I mean, it's actually possible to interpret it as the genius of a surface, even though this will not matter too much for us. And so what we do is, in view of this picture, we are taking the matrix which is defined there. We are centering in an appropriate way in order to make sure that its expectation, the expectation of the sum of its eigenvalues is 0. So for this, I have to divide it by, so after normalizing by over ds, I have to subtract a multiple of the identity. And I take this extra homothetic normalization. And then we have a nice formulation for the moments of this centered and renormalized version of the Wishart matrices. Namely, I can write the expectation of the piece moments. So actually this is just the sum. This is just the sum of the eigenvalues to the power p. And it turns out that I can write it as the sum. I didn't define this, but this is the collection of all permutations which have no fixed point. And you see, there is the interesting thing here is generically, as S becomes larger than D, which is what we are going to care about from now on, which will correspond actually to the case C larger or equal than 1, then this matrix is generically invertible. And of course, the converse is obvious. Obviously, S is strictly than D. Then the rank of the matrix is S, which is strictly than D. So it's not invertible. And so it turns out that if S is larger or equal than D, then we are summing two quantities which are some power some number between 0 and 1 to some integer power. So this quantity here is D over S is between 0 and 1. And if alpha has no fixed point, it's easy to check that absolute value of alpha, norm of alpha minus p over 2 is a positive number, and same for this d to the minus 2 genius of alpha.
The SP0?
Oh, so this means it's the collection of permutations which have no fixed point. And this is what ensures that this actually is going to be a positive integer. So we have this formulation. So there has been other formulation for this for a long time, but somehow here for what we want to do for what we want to prove, it's interesting to have the centered version. And so if you look at this and let the dimension go to infinity, you see that only the genius 0 will.
Flash us G alpha again for a second.
Which one?
The G alpha.
G alpha again. So it's the you see you have this triangle inequality, and this is the gap somehow. It's the violation of the inequality. And you can really see it as a genius if you look at the right folding of a polygon. Okay, and so basically, what this result implies, and what I'm just going to write here, is that if we assume that S over D, if we make the assumption that S over D has some nice behavior as D goes to infinity. So this is this number C. Then this implies that this. So this is what I said before. It's just a rephrasing of what I said before. That this converges towards the Wishart, the Marchenko-Pastor distribution, which is written here. And now what I want. So So already these gentle combinatorics are quite useful to say something. That's a history that has been long for a long time. It's been known for a long time that Wishart matrices have this asymptotic behavior. So I guess it's Marchenko and Pastor who did it. But now the point that I want to make to explain a little bit what's the difference between the behavior of mu and its support, even though let's say that I have this C equals 1 plus epsilon, what I have just proved so far, what I can just prove with what I said is that if I look, for example, at the percentage of eigenvalues which fall in this interval, which is slightly bigger than the support, then asymptotically the percentage will be 1, which means that I cannot rule out, for example, the possibility that there will be a small number of eigenvalues here, like let's say square root n eigenvalues, which are outside. It's just a number. What this result proves is just that the number of eigenvalues which are far away is small in comparison to n, to d, to the dimension. In other words, if I look at the support, which does not take care about the mass, there is a possibility that it still has some behavior in the limit which is different from what we expect it should be. So in other words, if I take this topological limit soup of the collection of supports, it is clear that it will contain the support of the limit, but in principle it could contain more, and somehow yes. So it's not clear. Basically, the whole question, the whole paradigm about the second question about the behavior of the support, and in particular here the largest and smallest eigenvalues, is what can we say about the converse? Is it true that we are going to have the converse behavior? In other words, will we have, yes or no, a small number of eigenvalue which misbehave from the asymptotic point of view? And so the proof, I didn't present the proof, but the statement that I presented as the analytic statement that I presented so far relies on combinatorics. Basically, if I can prove convergence of moments pointwise, then by some nice if I have some nice compactness arguments, then it will imply the weak convergence of a measure towards where I want it to converge. But somehow this pointwise convergence is not enough. That's the point to ensure to understand the behavior of the support. So we need something we need a little bit more of uniformity. So actually we need to look at moments k which grow a little bit in the same time as d grows. So here let me try to I try to write down an example. Let's look at and there is a typo in what I wrote. So let's look at the identity matrix. So this one here was meant to be the identity, was meant to have no epsilon here. So the point is that if I look at so I know that the identity matrix, its spectral distribution converges to the Dirac at 1 because I have all the eigenvalues which are 1. And I would like to see what happens if I have only one which is away. So let's look at the moments. If I fix k, if I put, let's say, an epsilon or an epsilon prime or the second epsilon to be 0, if I fix k and let d go to infinity, the behavior is the same, and this is perfectly coherent. It just says that the moments they cannot tell what happens with just one eigenvalue. However, if I just look at the computation, if k becomes big somehow, so the threshold I think is logarithm of d, then I will have this 1 plus epsilon to the k, which will not be absorbed anymore by this 1 over d. And at some point, if we take k large enough, as d grows to infinity, then we will start to see that the behavior of large moments, they can also take care of the outliers, of the eigenvalues which might misbehave and whom we want to rule out.
These two expressions.
There is a typo, like I said. There should be nothing here, or epsilon prime if you want. So sorry for the typo. Actually, this is not a proof here, but it's just some kind of. I mean, this turns out that actually you can prove somehow inspired by this argument without typo that if k, if it turns out actually it's an if and only if k is bigger than log d, and if you can understand things properly, then you will be able to understand the support of d. So it turns out that with the theorem that I wrote, it is actually possible to understand that. It's possible to raise k at the same speed. I mean, to infinity in the same time as d goes to infinity, and we obtain. So we obtain in the setup where s over d has an asymptotic behavior, that wd over d does not have this bad behavior that we were afraid of. That really the largest eigenvalue are close to a, and the smallest eigenvalues are close to b. And something else which is quite important for the purpose of quantum information, as we will see, is if S grows quicker than D, really quicker than D. So somehow more this means that C grows in the meantime. Then we have to make some extra normalization, and like I said, this was behaving like a semicircle distribution, and actually this is. So after making the appropriate normalization, this is actually the correct result here. So we have a combinatorial proof for it. I guess there was some analytic proofs of these results before, but I think that the proofs were really depending on the regimes of D and S. So here we have something which is simple and kind of uniform. So let me, as promised, let me start with one application which somehow puts sets some parallel with what Guillaume and Staszek are speaking about. So I will speak about this property in quantum information which is called absolutely positive partial transpose, so APPT, which just means that somehow my state in D of C1 and C of D1 and C of D2, so I have these two states. It is PPT, but actually it is PPT with respect to any tensor decomposition that I make. So I kind of forget of the tensor structure of CD1 and CD2. I just think I have CD1 D2, and I look at all ways I can write it like CD1 and CD2. So it just boils down to having a unitary matrix D. So here D is D1 and D2, and I'm asking for the property of being PPT.
I don't understand.
Okay, so
P of CD1 tensor CD2.
Okay, so it's a notation of a quantum information theoretic notation, which is so D of CD. This is the collection of matrices of D times D matrices which are positive and of trace 1. That's right. Just the notation. So here D of
so
C.
What's the relationship between D, D1, and D2?
And D equals D1 times D2. I should have said that, yes.
Oh, okay.
Okay. So, I don't know actually if it's a very useful notation, but that we can say something. So, clearly, APPT.
So what's the script? PPT?
Oh, PPT, positive partial transpose. So it means so PPT so A belonging to D of C D1 then C D2 belongs to PPT means that the transpose, the transpose, if I just take the transpose on, so this is a subset of MD1 times MD2, okay? And the transpose times identity of A is a positive matrix. So you see what I do is I have two legs of my tensor. On the first one I apply transpose, on the second one I do nothing. So this is that's a criterion which was mentioned yesterday, I think, to check separability.
You write the matrix as a block matrix, and you take the transpose of each block, but not of the whole matrix.
Let's take a counter example maybe. So if I look at this matrix, so which belongs to M2 times M2. What is the partial transpose here? Let's say that I'm taking the transpose inside on the big blocks and I do nothing inside. So here I get nothing. Here that guy is sent out there. That guy is sent out there. And so it's not positive anymore. You see the matrix with 1/2, 1/2, 1/2, 1/2, and 0 everywhere else is not positive anymore. So this is the negation of being PPT. That for example is going to ensure that this matrix is not separable. So okay, that's that. So there exists, although I'm not going to state it because I want to insist a little bit on the random matrix aspects. There exists a nice explicit algebraic characterization of being APPT.
Can I just ask, is it obvious that APPT is not empty?
Take the identity
Oh, the
first.
identity, of course.
Yeah.
That's what I was thinking first.
Thank you. Okay, so anyway, what happens is that we would like to see what happens. So again, we ask the same question as Guillaume was asking yesterday. We would like to see what is the likelihood that I end up having an APPT state if I pick it at random. So this boils down to for us, our setup is so I should have said before that D is D1 times D2, and we pick a Wishart matrix of parameters DS, and we want to check the APPT property for S. D tends to infinity. So pretty much what Guillaume was considering yesterday is when basically D1 equals D2 equals so which means P equals D1 equals D2. So I want actually to say something more general here. Actually, this is a typo. So this is just P equals mean of D1 and D2 is just a notation. And first, I'm looking at what happens when D1 and D2 go to infinity, and then we have a threshold estimate here, which is almost sharp. So basically, we see that if the parameter of the Wishart matrix is more than 4 times P squared and D, so again P squared is the mean of D1 and D2, then we have APPT. So of course we expect that the bigger, as was mentioned by Guillaume yesterday, we expect that the bigger S the more likely it is APPT because things concentrate more to the identity. And we have a full converse if D grows fast enough in comparison to P square. So this is a statement 2. Somehow this is kind of sharp. And when P square, and we have a partial, we have an almost, we have a partial converse when P square is as big as it can be. So we just lose some kind of constant. This is less than 1 actually here. This quantity. And here, interestingly, we can say something also when P does not go to infinity. So we can say something when P is also a fixed number. So let's say we would be interested in C D1 and C D2, and let's say D1 would remain a small number, and D2 would go to infinity. And that's the next slide. And in this case, if I write the threshold is going to be that S has to grow to the same speed as D, so S behaves like C times D, and the threshold is going to be if C is bigger, or I mean, is exactly going to be P plus square root of P square minus 1. And all this actually, if you look at the algebraic characteristic, it's very closely on the linked to the previous term that I quoted about the behavior of largest eigenvalues in the case where, for Wishart matrices, in the case where S goes to infinity faster than D. Okay. So that's what we can say already. I mean, we can say many things for the case of one single matrix and the support, the arithmetic behavior of the support. Now the next question is.
You can say a word for somebody who's like totally out of this. What's the interest in this property APPT?
Can anybody help me here?
I mean, you proved a theorem about it, so you must have some interest in it.
In the case of qubits, where you just have 2 by 2 tensor 2 by 2, that's a necessary and sufficient condition to check for entanglement. For higher states, it's sufficient. It's necessary, but not.
Yeah. So yes. Okay. One way you can think of it.
There are a number of important conjectures about things like bound entanglement that can be restated in many ways that are associated with this PPT.
Yeah. So one thing you could say about that, I mean, I can give also a partial answer to your question. Somehow, when you want to check entanglement or even the positive partial transpose, it turns out just looking at the eigenvalues of the state is not going to be enough. However, the APPT property depends only on the eigenvalues. So you can just look at the eigenvalues on this side. So somehow it's a faster criterion in some sense to you just look at the eigenvalues, and if it says APPT, then it says PPT right away.
Actually obvious that there are states in APPT that are not separable.
Maybe I guess the threshold stuff should answer that question, right?
I mean, is there like an example, like the identity in Beth's question before?
Yeah, that's
The identity is clearly in APPT, so the set is non-empty. But are there non-separable states in APPT? And if so, is that obvious?
I can't think of an example right now. I think that the threshold for APPT is not as is different than the one for separables. But
Like bigger.
oh,
Well, yeah, it's very different.
Is it even obvious
But
that?
it's bigger. It's bigger than separable.
Yeah, is it even obvious that all separable states are in APPT, because you
No,
could
no,
be an
no.
entanglement.
yeah, no, that's
There is an
fine.
analogous ASIP.
Yeah. So there is also a definition of ASEP, which we could give the same definition for ASEP, but actually, I think they think.
That's Matthias's
way.
question. Yeah, they're different.
Yeah. So they're,
And if so, what is an element in one and not in one?
What about their separables in this range of parameters, the random states?
Could you go back one slide?
yes.
I mean, to the previous
There are
previous.
common states
One more.
are in APT, for example.
Sure, no, but the question was already
Where you have the statement of the threshold. The one on which you have the threshold.
States in
Untitled.
APT.
The next
For
slide.
pieces, right, or possibly
No,
equal to.
no, that-
No, the one with the theorem.
Yes, this one.
Yes.
Yes. So I don't know the answer to your question.
Already that is
But that looks like a very good question. Okay, so let me quickly say something about. I've said one half of what I wanted to say. So now I want to say quickly. I will have to accelerate, I guess. What happens if we take a bunch of IID matrices and we take non-commutative polynomial in them? So let just as an example, let's say that for some reason I would like to understand what happens. So I pick two copies of a Wishart, and I would like to understand what happens to W1, W2 plus W2, W1, or anything like that. So it's just a theoretical problem at this point. And the method of moments, which I described quickly, allows us actually, it turns out, to understand what happens to the limiting behavior of the eigenvalues counting measure of this random matrix. This is something which is very well understood, which has been done by Voiculescu. So I want to say something about it, but I will probably skip it. However, the limiting behavior of its support. So we have the same problem as here. Can we have some eigenvalues which misbehave or not? Is much more difficult to understand. And in the case of a single matrix, we could let the moment grow to infinity in the same time as D. Here, in principle, we could do it, but we don't know how to. It's just too difficult somehow. So I just wrote that there is this C-star algebra versus von Neumann algebra problem. Somehow the mu D and the problem of mu D is some kind of problem of ultra product of von Neumann algebras, and the understanding of norms is more like a C-star algebra product of C-star algebra nature, and it's just more difficult. And there is one technique for it. So the moment technique should work, but we don't know how to make it work. So there is instead a very nice operator algebraic trick, which I want I still want to introduce this trick. It's called the linearization trick. So actually, it's something which has been known for many years, but it has been used for the first time successfully by Hargrup and Torbjørnsen in their seminal paper on the norm of convergence of random of independent GUAs. And basically, I'm not going to write this here, but rather say something which is virtually rigorous, which says that understanding the supports for all non-commutative polynomials. Here I'm just taking two independent copies, but it could be as many as you want actually. So not only the one which I gave, but you just take the bunch of all non-commutative polynomials that you can make, and then you say, I want to understand simultaneously how all this guy behaves as the dimension goes to infinity. This is actually, it turns out, equivalent to understanding the collection of all supports of quantities which do not lie anymore in the D by D matrices, but in the MK times MD matrices. So what I do is I'm going to take A0, A1, A2, which I'm going to call matrix coefficients. So this is self-adjoint matrices in MK. And then with this I cook up a new random matrix which lies in MK times MD. And if I can understand all these supports for all coefficients, all K, then this is equivalent to understanding all the supports of all non-competitive polynomials. This is surprising because this is two very different quantities, but it turns out that it's the same. And so let me comment a little bit on that. So the advantage is that we don't have to deal anymore with non-commutative multiplication. This is why this is called the linearization trick. But of course we have to pay a price for this, and it can be an expensive price. Actually, it depends. It's to allow matrix coefficients instead of just complex coefficients. And also something important for the purpose of quantum information theory, we have also to give up understanding the speed of convergence. Somehow it's a global equivalence between two things, and there is no well understood quantifiers of how to fine tune the equivalence between the two things.
Previous slide for a second.
Yes. So we have this equivalence of understanding the spectrum of all of the collection of all non-commutative polynomials with this linear coefficient stuff. There is, however, a very important bonus to this equivalence, is that if actually we can understand one or the other, then for free we can understand even more, which is non-commutative polynomials with matrix coefficients. So it even says that if I can understand all the non-commutative polynomials, I can automatically understand all the non-commutative polynomials with coefficients. So I can actually understand much more for free. And so this is going to be quite useful in the applications. So let me just, so I wanted to say something about random matrices, but about free probability, sorry, but maybe it's not a very good idea. Maybe I should rather, okay, let me see if I can survive without it. So, I mean, probably what matters is this at this point. I will just try to see if I can just present this theorem. So the theorem is the following. We are going to assume that we have a set of matrices. Actually, I call it a set of quantum matrices, but it could just be a set of random matrices, WID, which admits a joint limit distribution. So joint limit distribution just means that if I take any non-commutative polynomial, and if I look at its mu d, then its mu d has a limiting behavior. And then the theorem says that if I enlarge this set WID with some random unitary matrices, which are all chosen randomly independently from the WID, then the enlarged test set still has this property that it admits a limiting behavior. So it's some kind of bootstrapping theorem. Somehow I start with a set, and then if I throw in some extra independent random unitary matrices, I still have some nice behavior, and the behavior actually can be computed with these free probability techniques which I skipped. So let's just say that there exists a technique for this. But once again, so this was a really important result, which was proved by Voiculescu. First proved a Gaussian version in 92, and then a full version in 1998, and it really had a very big impact. But as before, he did not say anything about the possibility that a small percentage of eigenvalue could misbehave, and this is what we had to address by this notion of strong convergence, which basically says that not only the mu d's should behave well, but also the support of mu d's should behave well. And the theorem that we obtain, so it looks a little bit, maybe I'm going a little bit too fast, but I would still like to say something about applications. So somehow the idea is, what Voiculescu said is, if I have a set of random matrices, and if I add one extra or as many extra IID unitaries as I want, then the enlarged family still has a nice behavior as the dimension goes to infinity. The histogram of eigenvalues still has a good behavior. And what we prove actually is that if on top of that we assume that not only the mu d's have a good behavior, but also the supports of mu d has a good behavior for the initial family WID, then adding these independent unitaries will still not change this property of having a strong convergence. So as Voiculescu tells us under these assumptions, we still have a good behavior for the mu d's for the family, for the extended family, but also for the support. And this is actually a result which we proved 2 years ago with Camille Mal, which extends the big result of Hagerup and Fabianson. And let me just finish by mentioning 2 applications of this result to quantum information theory. So I'm echoing a talk that Ion made in September, where he presented a joint work with Theo Banica, in which they look in MD times Mn. So here it's not D1, D2 it's D times N, and then they take the partial transpose to this set, and they check what happens as D goes to infinity. So N here is fixed, D goes to infinity, and there is an environment which is of dimension D times M, and then you take the partial. You have this random pure state. You take the partial trace with respect to the environment. Then you get these normalized Wishart matrices. And what they prove is that this, as D goes to infinity, this converges towards some distribution, which I'm not going to describe. I'm just going to say that they proved that the spectrum of this distribution is positive if and only if. So you see, we have 2 parameters in the problem. We have N, which is the fixed size space, and we have N, which is the relative dimension of the environment. And the point is positive, that the spectrum distribution is positive if and only if we have these 2 conditions. N is less than M over 4 plus 1 over M, and M is greater than 2. So what was very nice about this result, about their result in practice, is that if these conditions are not satisfied, then automatically we know that typically this is not going to be PPT, because what they get then, they know that they have a limiting distribution which asymptotically goes to the left, has some negative support too. So which means that there is a strictly positive percentage of eigenvalues which are here. So we don't even care about whether there are some eigenvalues far away. We just know that there is a strictly positive percentage of eigenvalues which are there. So they have one direction somehow, that PPT does not hold with high probability if one of these conditions is violated. But the converse was not available, because what happens if the conditions are satisfied and the limiting distribution is like this? Do we have PPT or not? Well, maybe not, if we still have a few eigenvalues which are negative. However, we proved with Camille that this is not going to happen. So somehow, one of the application of our multi-matrix setting is that this is sharp, that PPT will hold with high probability if these conditions are satisfied. So that they have exactly the sharp things here. And well, okay, so let's see. Okay, maybe I will still say this very, very fast. This is my last slide. So some very different application now. to the theory of random quantum channels, so which we were looking at for the purpose of minimum output entropy, the study of the minimum output entropy violation. So now I'm taking a random projection which belongs to mk times md, so k is fixed, d goes to infinity, and I assume to have the property that for all matrices A in mk, so k is fixed once again, the pair of matrices pi d and A times 1d, which is a matrix in mk times md, it has a strong limiting distribution. So in the sense that all non-commutative polymers behave well, and also the supports behave well. And as we know, we have lots of examples of this. I'm going to speak about this. So if I have this projection, I get for free a channel which goes from the endomorphism of the image of pi d to mk just by taking the partial trace. And now if I take key to be any other quantum channel, then what we prove is that with Motov-Kuda and Ion Nekita is that if I look at the image under the family phi d of all pure states, then it converges strongly to a convex body, which is the dual in the sense of Guillaume of this convex body here. And the interesting thing here is that actually the same property is going to hold true if I look not only at phi d, but at the family phi d, but at the family phi d times chi. So in other words, we can understand simultaneously what happens to a family phi d and the family phi d times something else. So in principle, it opens the door to understanding what happens to the tensor product of quantum channels in the meantime, provided that this second one is fixed. And so some applications of this, the first sub-example of this is if pi 1 is just a random projection, just taken according to the uniform measure on the Grassmann manifold, then after making the computations, we obtain this violation of minimum output entropy additivity, this large minimum output entropy violation. So I'm not speaking about it today. And the other one is that if we look at the unitary channel, the channel that to X takes the convex combination of UI, X, UI star, where the UIs are chosen at random, so the mixed unitary channel, I think it's called. Well, what we have is that we can also understand very well some property of this channel, and this channel is more or less the channel that was used by Hastings, so that's it matters a lot. And for example, this is, we can tell many things about this thanks to the previous stuff, but in particular, we can say that the norm S1 to S infinity is exactly this quantity, 4k minus 1 divided by k squared. Okay, and I think I'm over time, so I'll just thank you and finish with references.
Thank you very much. More questions? I have one. If you just go back, so this one, yeah, this example. What about the ISP? I mean, the output P norms?
In principle,
I thought when you have this body.
You see, the problem is that we need to understand what the value of this is. That's our problem, and in principle, it's possible to compute it. I mean, there exist in principle techniques which were developed at the intersection of free probability theory and the operator space theory, but it's very difficult to implement. Actually, it's some kind of amalgamated free probability techniques. So already the setup of here was already of example 1 was already just making the actual computations which lead to logarithm 2 was extremely difficult, and this looks even more difficult somehow. So it just turns out that the L infinity case is a little bit simpler because there is some results on zeta algebra of free groups which can be used there. But,
Nobody else has a comment or a question? Let's thank Benoit.